Hello and welcome. This is going to be our lecture video for the second semester final test review. Let's go ahead and get started with problem number 1. What is the kinetic energy of a 22 kilogram printer moving at a velocity of 8 meters per second? For this, we need our kinetic energy formula. So kinetic energy equals 0.5 times mass times velocity squared. Right, because it's squared, velocity will have a greater influence on the kinetic energy here. So let's plug in what we've got. We've got a 22 for our mass and an 8 for our velocity. Put all of that into your calculator and you get 704 joules. All right, next one's another kinetic energy problem, but we've got a slight hiccup, and that's that our mass is given in grams, while the formula requires kilograms to give us joules. So we need to do a quick little conversion. 10 grams times our conversion factor, that there's 1,000 grams in 1 kilogram. And we'll get that 10 grams is equal to 0.01 kilograms. And now we can just plug it into our formula just like we did the last one. 0.5 times 0.01 times 343 squared. And let's see what we get there. And I got 5,882 joules. All right, so much more energy with this small object moving much, much quicker than the big object in the problem up above. All right, gravitational potential energy. So the formula for that is mass times g times height. And for g, we're always going to use 9.8, which is our approximation for the acceleration due to gravity on Earth. Mass should be in kilograms, so 35 times 9.8, and then the height should be in meters, so 40 is just fine for that. 35 times 9.8 times 40, and we get that we have stored up 13,720 joules of energy. That's how much energy would be released if we were to allow it to drop these 40 meters. All right, bag of potatoes. So it's moving, so we're going to use our kinetic energy formula again. 1/2 mv squared equals our kinetic energy. But now we have a different arrangement of variables. We know the energy is 5,380 joules, so that'll come in over here for kinetic energy. We don't know the mass, we'll leave that as m. The velocity is 77, and we know that that's squared. So what we plug into our calculator is everything except for the m on this side, the 0.5 times 77 squared, and we get 2,964.5 is all of those numbers. It still times the mass, equals 5,380. And then we'll divide both sides by that 2964.5. 2964.5. And we will get 1.81 kilograms. So not a very big bag of potatoes, but that's what the math tells us. All right, problem number 5 tells us that we've got an escalator moving passengers, a certain number of passengers every minute. We're going to try to figure out the power requirement of that escalator. So the power into the escalator will be the energy that it gives to these passengers, but that energy will just be stored energy in their new gravitational potential energy. So let's figure out what the new gravitational potential energy is of these passengers every minute. So the first thing we should do is take the average mass, 54.9, and multiply by the 20 passengers. 54.9 times 20 gives us that we are going to move within 1 minute 1,098 kilograms of passengers. And now we're going to use our gravitational potential energy formula, mgh. That will go in for our mass. G is always 9.8. And these passengers are getting moved up 5.2 meters. So now multiply that number times 9.8 times 5.2 to get that all of the passengers together will have 55,954 joules of now gravitational potential energy that they didn't have before. But that took 1 minute. So let's divide it by the 60 seconds that are in 1 minute, because a watt is a joule per second. And then that gives us our final answer of 932.6 watts. All right. For ideal mechanical advantage, the only work that is actually done is work that is in opposition of gravity. So the 5 meters is the work that was actually done, but we got to push it 24 meters up this ramp to accomplish that 5 meters. So each meter we're pushing it, we're only accomplishing a small amount of the total of the actual work done against gravity. So that means it takes a lot longer, but we get a mechanical advantage. To find the mechanical advantage, it's just as simple as dividing these two numbers to get that we get a 4.8 mechanical advantage. So ideal mechanical advantage, meaning that if lifting this box directly would take 48 newtons of force, we could do it with only 10 newtons of force up this ramp. All right, what are the 3 types of levers? So they are class 1, class 2, and class 3. Class 1 is your typical seesaw, where the load and the effort are on opposite sides of the fulcrum. All right, so we will just use a seesaw as our example of a class 1. Class 2, you put the fulcrum at one end. You put the load in between you and the fulcrum, and then you put your effort further out on our lever arm. And this gives you a mechanical advantage. So this is something like a nutcracker. A nutcracker gives you a mechanical advantage, so greater force, which helps you, crack walnuts. And then a class 3, you put your fulcrum at one end, but then you put your effort close into the fulcrum, and then your load further out. And this gives you a mechanical disadvantage, but what it does give you is greater speed out at the further end of the lever arm. So if speed's what you're after, you want a class 3 lever. And so this would be like a baseball bat. All right, number 8, how many calories are needed to heat 40 grams of water 10 degrees Celsius? It's as simple as this, 40 times 10. So 400 calories. This is the definition of a calorie, is it's the energy needed to raise 1 gram of water 1 degree. So 40 grams, 10 degrees would be 400 calories. All right. A food contains 300 calories. Notice the capital C here. That's actually important. How many joules of energy, this is every, but energy does it contain? So let's just do a unit conversion. We have 300 big C calories, but there are 1,000 little c calories in every 1 big C calorie. So other countries call them kilocalories, but we just call them big C calories. And then in every 1 little c calorie, we find 4.184 joules of energy. Multiply everything across the top. And we get a very big number, 1255 0.200. So 1,255,200 joules of energy. Food is incredibly energy dense. Just 300 calories, and that's enough energy to do a lot of work. All right, number 10, we have to do some labeling. We've got a heating curve here. So in section 1, our object is solid. Then in section 2, it is melting. In section 3, it's a liquid. In section 4, it's boiling. And then in section 5, it is a gas. So if this was water, it would go from ice to liquid water to water vapor. And it would reach these plateaus as it's undergoing those phase changes. All right, the melting point is the temperature needed to melt it. So the melting point would be over here on our y-axis. Right there is your melting point. It is a temperature. Freezing point is the same. So melting point slash freezing, just go in the other direction. Boiling point is up here. So that's boiling slash condensing. All right, heat of fusion is the distance down here. So how much heat actually went in to cause that fusion. This is our heat of fusion. And it's a number. It's the number of joules that we needed. And then the heat of vaporization is the distance of number 4. Right there, the heat of vaporization. Where is it increasing kinetic energy? So increasing kinetic energy, that's sections 1, 3, and 5. And then increasing potential energy. That was in sections 2 and 4. So temperature is a measurement of how much the molecules are actually moving around. So higher temperatures means the molecules are moving faster, and if anything's moving, that's kinetic energy. All right. Number 11, a 25 kilogram metal ball is heated 200 degrees with 2,330 joules of energy. What's the specific heat of the material? So the formula we need is the specific heat formula. Q equals MCAT, MC delta T. So the energy needed was 2,330 joules. We'll put that in for Q. The mass was 25 grams. The specific heat is unknown. And then the change in temperature is the 200. It was heated 200 degrees. All right, we'll multiply the 25 and the 200 and then divide it to the other side. And I get a specific heat of 0.466, and the units on that is joules per gram per degree Celsius. We had to do per gram because our mass was given in grams, not per kilogram. All right. Number 12, we have to do a calculation that has 3 parts. So water or ice is heated into liquid water. So that process is going to involve 3 steps. The ice needs to warm up to 0 degrees, which is the melting point of ice, or the freezing point of water. It needs to undergo that phase change, and then it needs to heat up again. So it needs to go from -20 to 0, and then from 0 to 50. And this is 3 separate sections. All right, so for that first section, we'll just use Q equals MCAT, but for our C value, we'll use the C value for ice up here. So Q equals our mass. The C value includes kilograms, so we better write our mass in kilograms, 0.5 times 2,900, or 2093. And to get up to the melting point, it needed to change 20 degrees. All right, then in the phase change, we don't have to multiply by any temperature, but we still multiply the mass times the heat of fusion right there, 334,000. And then the last section, it's another Q equals mc delta T. Its mass is 0.5 kilograms. The specific heat of liquid water is, well, 4,186. And then that liquid water is going to change 50 degrees to get to its final point. So multiply these and add them all up, and what do you get? You should get 292,580 joules of energy was needed. All right, number 13 is similar, but we're going from liquid water now to vapor. So let's just draw a quick little curve here. So it's 30 degrees. It's going to end at 150 degrees. You have to know that water boils at 100 degrees. So 100 will be our stopping point in here on our way up to 150. And let's write out our three sections. So 400 grams is 0.4 kilograms. Specific heat of liquid water is 4,186 joules per kilogram per degree Celsius, and this liquid water changed 70 degrees. Then we need the heat of vaporization, which is this very big number, 2,260,000. And then for that last section, the specific heat of steam, which is the lowest number, 1,996. And then the steam heats up 50 degrees. Let's multiply all three of these. And I got 1,061,128 joules of heat is needed. All right, number 14, what is entropy a measurement of? One simple word, entropy is a measurement of disorder. All right, and sort of based off of math, that because there's more ways for something to be disordered than ordered, matter will always seek disorder. So number 15, does entropy naturally increase or decrease over time? It always increases. Matter seeks disorder. Give an example of entropy in your daily life. Your room gets messy over time. There's more ways for your room to be disorganized than organized, so it will naturally become less organized over time if you don't actively try and clean it. All right, heat transfer, so convection. This is through a medium. And it's typically air. It could also be water. So, just like a fan blowing heat. Conduction is heat transfer through touch. So they have to be directly touching. For the heat to transfer, that is conduction. And then radiation is through electromagnetic waves, typically in the infrared spectrum. And that's like how the sun brings heat to the earth. All right, 17. A mosquito buzz is often rated with a decibel rating of 40 decibels. Normal conversation is often rated with 60 decibels. How many times more intense is a normal conversation compared to a mosquito's buzz? So every 10 decibels is 10 times louder. So 20 decibel change is 100 times louder. 30 decibel change is 1,000 times louder. So the difference between these two is 20 decibels. So that's 100 times louder. All right. So using this table, how many times more intense is the front row of a Smashing Pumpkin concert than the 15th row of the same concert? So 15th row is 100, so that's a change of 10. So that's just 10 times. Average factory, well, that's a change of 20. We just saw that. 20 decibels is 100 times. Normal speech is 60. So 50 decibels would be 100,000, 100,000 times less intense. So, you take the change in decibels, divide by 10, that's how many zeros you should add to a 1 for how many times louder it is. It can be really useful to have a table like this on your review. Maybe it goes up to like 60 to show how many times louder it is. It goes 10, 100, 1,000, 10,000, 100,000, 1 million. And that's how a logarithmic scale works. All right, number 19. Automatic focus camera is able to focus on objects by using an ultrasonic wave. So it sends out a wave to reflect off the image, and then the sensor detects how long it takes to return. Speed of sound is going to be 340 meters per second, wherever we are. It does change with temperature, but where we are, it's 340. And it takes 0.25 seconds to hear the echo. So what distance did it travel in that? So distance equals speed times time. We don't know the distance, but we know the speed is 340, and we know the time is 0.252 seconds. So multiply those two numbers. And we get that the sound traveled 85.68 meters. But that's how far it traveled. It needed to go there and come back. So divide that by 2 to get that our object is 42.84 meters away. 20, true or false, doubling the frequency doubles the speed. That is false. Speed is set by the medium. You cannot change the speed by changing your frequency. All right, number 21. So we've got a frequency of a sound on a keyboard is 256. We know the speed of sound. We're trying to find the wavelength. So we just need to use this formula here, that velocity equals wavelength times frequency. We know the velocity is 345. We don't know the wavelength, but we know the frequency is 256. We'll just divide both sides by 256. So 345 divided by 256 gives us a wavelength of 1.35. And because the speed was in meters per second, the wavelength is in meters. All right. Speed of sound on a cold winter day. So there's a formula for this also in our formulas, that speed or velocity equals 331 plus 0.6 times the temperature. The temperature is 4 degrees out, so we'll plug in a 4 right there, and then solve. So 331 plus 0.6 times 4 gives us a speed of sound of 333.4 meters per second. All right, so looking at this, at which points would constructive interference occur? So constructive interference is where you have like two wave crests making an even bigger wave. So we're looking for where either two bold lines or two thin lines overlap. And it looks like that happens at A, B, not C, not D, not E, and not F. So I think it's just A and B. Everywhere else, I see destructive interference. An antinode is where we have destructive interference canceling out. So that was points C, D, E, and F. So there are 4 points that represent antinodes. All right, number 25. So you're standing on a rail station. A train is approaching and it's gradually slowing down. So the horn makes a frequency of 300, but we got the Doppler effect happening here. So because it's moving towards you, we will hear a pitch higher than 300. And it will slowly lower to 300. So slowly lowering to 300. So I just literally picture those sound waves getting stacked up because they're moving away from the train that's moving in the same direction. And so because they're closer together, it'll be perceived as a higher frequency. All right, number 26, we're on to light. So looking at this diagram, what's the angle of incidence? We always measure off of the normal, and we've got little arrows to show us how the light came in here. So the angle of incidence is B. Angle of reflection, also measured off the normal, is going to be C. Angle of reflection here, again, we have to add in our own normal, then measure off of that. So if the normal is at 90 degrees, this would be 60, this would be 60, and it's this 60 right here is the angle of reflection, so 60 degrees. All right, so we've got a bunch of students below the mirror, and then the reflected images above the mirror. To figure out if somebody can see somebody, you need to be able to draw a straight line between them and the image, and that line has to go through the mirror. So let's see if I can find a straight line. All right, so as we go to answer the question, all the people D can see, we're going to draw a straight line from D and see who it hits that goes through the mirror. It definitely hits psi's reflection, so we'll definitely want to include psi. If D can see herself, so that's not always true. Sometimes you can't see your own reflection, but you can see other people's reflection. We can draw a straight line to Ed's reflection, and let's just see if we can draw a straight line to Fred's reflection. If we do, it doesn't go through the mirror, so it looks like it's only these three people. Yep, none of these other straight lines work. So all of the people that D can see was psi, herself, and Ed. Who can see the most people? It's Ed. Standing very close into the center of the mirror helps you see the most in the mirror. And who can be seen by the most people? It's also Ed. If you can see someone, they can see you. That's just a very basic property of mirrors. Okay. All right, so if Usain Bolt runs at a mirror at 10 meters per second, Bolt and his image will approach each other at 20 meters per second because they're both moving towards each other, so we add their speeds together. Surface of a concave mirror is pointed towards the sun. Light from the sun hits the mirror and converges to a point. If the converging point is 20 centimeters from the vertex, what's the radius of curvature? We just need a very simple formula for this. I think I need to actually add it to your formulas, but it's the focal length. Well, if you double the focal length, so 2f equals the center of curvature. So if it's converging at 20 centimeters, the center of curvature is 40 centimeters. All right, next problem. So the diagram below shows two rays emanating from the top of an object. Draw the reflected rays and make sure they both go through the image point. So first we got to find that image point. So we need to use some straight lines again. So the first straight line we're going to use is just one that is parallel to a radius of curvature that then bounces. And because it was parallel, it's going to go directly through the focal point. Only parallel light goes through the focal point. Let's try it coming out here. The next ray of light that we're going to draw is going to go through the focal point, and because it went through the focal point, when it comes off of the extension of the mirror down here, it will, get our line, be heading out totally parallel, giving us an image point way out here. So now every other ray of light that comes off of the point of this arrow will also go through that image point. So let's draw the reflection of that top ray. Once it bounces, it will go to that image point. And now we'll draw the reflection of that bottom ray. Once it bounces, it will also go through this image point. Everything is converging out here at the image point. All right, now 32, determine the image distance and image height for a 6 centimeter tall object placed 35 centimeters from a concave mirror with a focal length of 12 centimeters. So here we need to use our lens formula, which also works for concave mirrors. 1 over the focal length equals 1 over distance to the object plus 1 over distance to the image. All right, so the focal length here is 12. The image distance is, well, we don't know the image distance. We know the object distance is 35, and then we're going to solve for the image distance. So to do this, I'm just going to do 1 divided by 12 in my calculator. Then I'm going to subtract 1 over 35 and then invert that number to get that my image distance should be 18.26 centimeters. Now to get the image height, we have to figure out the magnification here. And our magnification formula is just di over do. So di over do is 18.26 divided by 35. And so we get a magnification of 0.52. And then we'll multiply that by our original height. It was a 6 centimeter tall object. So now the height is going to be 3.13 centimeters. All right, number 33. I gotta delete these. All right, 33. So we've got an image located 33 centimeters from a mirror, so that gives us the distance to the image of 33. The focal length is 11, so we can plug these into our lens formula real quick. 1 over 11 equals 1 over do plus 1 over 33, and then just do 1 over 11 minus 1 over 33, and we invert that, and we get the distance to our object of 16.5 centimeters. And determine the object distance and then whether the image is real or virtual. This would count as a real image because we could put a screen there and capture the image. The light is actually converging where it looks like it's converging. All right, number 34. An inverted image is magnified by a factor of 3. So we know magnification equals 3. And the object is placed 10 centimeters in front, so the distance to our object equals 10. The concave mirror, determine the image distance and the focal length of the mirror. So one of our formulas for magnification is di over do. So if di over do equals the magnification, we can figure out our image distance here. So di over 10 equals 3 times 10 times 10. We'll get that our image distance is 30. All right. Focal length. So now we're going to use our lens formula again. 1 over the focal length equals 1 over di plus 1 over do. And now we know di and do. We know DI is 30 and DO is 10. And then I'll just do 1 over 30 plus 1 over 10. Then invert that number. And I get a focal length of 7.5 centimeters. And this was 30 centimeters for our image distance. All right, we've got this diagram here to help us answer the next four. We're trying to figure out which objects are going to project their images into which sections. So I'm going to do it the other way around, starting with the objects and then figuring out where their image is going to go. So let's look at number one. Number one, all we need is two rays to figure out where its image is going to go. We'll have a parallel ray that goes through the focal point, and then we'll have a ray that goes through the focal point that reflects out parallel. And although I've drawn this really bad, I think that one is going to reflect into, I think it's into section S. All right, so which object will project into section S? It was number one. All right, object two here, this ray will look very similar, but then this one will bounce much wider and then it will project into R, so that's object two. 4 is very similar, but it'll reflect into M. That's not one of our options. All right, now 5 and 3, these are the ones that create virtual images, so they're a little bit more tricky. With 3, which is on the convex side of this mirror, we can draw a line that looks like it's going to go to the focal point. When this one reflects, it will come out parallel, but it will look like it came from over here in P. And then we can draw a parallel ray that will look like it went through the focal point, and both those intersect in section P. So 3 gives us an image in section P. And then we're process of elimination, we know it's 5 for the last one, but let's just see why 5 projects an image into W. So we can draw a ray that looks like it came from the focal point, and that will reflect out parallel, but it will look like it came from over here in W. And then we can draw a parallel ray that will look like it came from the focal point, and again, intersect out in W. So yeah, those virtual images are kind of tricky. When you've actually got some space to draw it out with a ruler, you can make it look a lot better than this drawing here. All right. So virtual image, I already said it. It was objects 3 and 5. When you're really close into the mirror is your best chance to create those virtual images. Everything else was a real image. You could put a screen there and capture the image. All right, and finally on to some electricity. So number 40, we've got some different charges here. So this is likely Coulomb's law. Force equals K times charge 1 times charge 2 divided by radius squared. So we're trying to find the force here. The K is just a constant. It's 9 times 10 to the 9th. There's more decimals there, but we'll just leave it like that. Charge 1 is -2 times charge 2 is 3. And then the radius is 80 meters squared. We can just plug all of this into our calculator and see what we get. And we get a very large 3 times 10 to the 14th newtons. That's a 14th newtons. So very large charge. And that would be towards one another because a positive and a negative charge are going to attract one another. All right, 41 is the same formula, but we're given different parts of it. So Q1 times Q2 divided by radius squared. We've got a force of 9 newtons. We know K is 9 times 10 to the 9th. We know one of the charges is 0.0005 And the other charge is unknown, so we'll say it's x. And then they're 10 units apart, so 10 squared. So as I plug this into my calculator, I'm going to do the 10 squared, which is 100, and multiply that to the other side. So now I've got 900 on the one side, and I'm going to divide away the other numbers. So divide by, in parentheses, 9 times 10 to the 9th. And then I'll divide away the 0.0005. And I'll get 2 times 10 to the negative 4th, which would be 0.1232 coulombs of charge. And it's an attractive force, so it should be opposite signs because opposites attract. All right, another one with Coulomb's law. So both the charges are -3. So I'm going to start filling it in. 9 times 10 to the 9th. And then -3 times -3. And then we don't know the radius here, but we know that they're pushing each other apart with 19.2 newtons of force. So to solve for the radius here, I'm going to do a little rearrangement and just get radius squared equals these three things multiplied, 9 times 10 to the 9th times 3 times 3. So that's 8.1 times 10 to the 10th. So let's say I multiplied that, so I should divide by the 19.2, so divided by 19.2. And then I'll take a square root. So divide by 19.2, and then I'm going to take a square root to get that they are separated by 64,951 meters. All right, for number 43, we need to know the definition of an amp. So 1 amp equals 1 coulomb per second. So 3.6 amps would be 3.6 coulombs per second. So 3.6 coulombs per second times 15.3 seconds will give us how many coulombs of charge. And I get 55.08 coulombs of charge. Now we need to know that 1 electron has 1.6 times 10 to the negative 19th charge. So take that number and divide by, in parentheses, 1.6 times 10 to the negative 19th. And we will get a very big number, 3.44 times 10 to the 20th electrons. On to 44, so it's saying potential difference. So we know it should probably be Ohm's law. So let's just write down V equals IR. So potential difference is the volts. The current is 8 amps, and the resistance is 12 ohms. So 8 times 12 means we've got 96 volts of potential difference. All right. What is the current through a 400 watt electric appliance? So watts, here we use a slightly different definition. So power measured in watts is just current times voltage, or times voltage. And so if we know the power is 400 watts, we can find the current. If we know the voltage is 120 volts, so 400 divided by 120 gives us 3.3 amps of current going through this appliance. All right. Find the total resistance. This one's very easy because they're in series. We just add them up. 12 plus 4 plus 6 equals 22 ohms. All right, in the next one, they're in parallel, so you have to add them up like this. 1 over 12 plus 1 over 4 plus 1 over 6, and then you've got to invert it again because that gives you 1 over the total resistance. So 1 over 12 plus 1 over 4 plus 1 over 6, and then I invert that number, and I get that this would give us 2 ohms of resistance. All right, find the current through this circuit. So let's find the total resistance by just adding those up. That looks like 31 ohms of resistance. And then we'll use Ohm's law, V equals IR. This is a 10-volt battery. We don't know the current, but we know the resistance is 31. Divide both sides by 31. And I will get 0.32 amps. All right, and for 49, we got to find the total resistance. So 1 over 15 plus 1 over 10 plus 1 over 6 equals 1 over the total resistance. So 1 over 15 plus 1 over 10 plus 1 over 6, invert that number, and I get that this branch here would offer 3 ohms of resistance. Then V equals IR. 12 equals the current times 3, so the current must be 4 amps. All right, now what do we do if there's kind of a combination? Well, let's figure out the resistance of the parallel by doing 1 over 15 plus 1 over 10 equals 1 over that total resistance. Then invert that, and we get that this section here will offer 6 ohms of resistance. Add it to the other 6 for a total of 12 ohms. And then V equals IR, 32 volts times 12 ohms of resistance. So 32 divided by 12 gives us a current of 2.67 amps. All right, we'll call that good there. That's that for this lecture video. Have a good rest of your day.